Hello students, welcome to Saurav Sir classes. The first question is, which of the following statements is not correct concerning the probability distribution of a continuous random variable? Option A, the vertical coordinate is the probability density function. Okay, so let me first draw the graph of a continuous probability density function. So the graph is something similar to this. It's actually this. The lines may not be straight. Now the x-axis, this represents the range of the variables, whereas the y-axis, this represents the probability. Now remember that the y-axis, that the coordinate for y-axis can never be negative because the probability is always positive. So it will be always above the origin, that is, probability would never be negative. So option A, the vertical coordinate is the probability density function. This is true. The range of the random variable is found on the x-axis. So all the possible, all the favorable events, or say the sample space, occurs on the x-axis. So the range of the random variable is found on the x-axis. This again is true. The total area represented under the curve will be equal to 1. Now the probability of all the possible events occurring, so if we sum the probability of all the events, well, actually some or the other has to occur. So the total probability is 1. So again, this area is true. The area under the curve between points A and B represents the probability that x is equal to A. Well, this is false because, firstly, remember that for a continuous random variable, point probability is equal to 0 for continuous random variable. And again, if, say, let us take this to be point A and this to be point B. So what this area actually shows is the probability that x less than equal to b minus probability x less than equal to a. So again, you can also write this as a less than equal to x less than equal to b. Thus this is false. The area, and option E is, the area under the curve represents the sum of probabilities for all possible outcomes. Well, that's what I said. Previously I have been saying that the area is the possibility that the probability between points that x greater than is equal to a and x less than is equal to b. Say if we take the points A and another arbitrary point C, then this represents probability a less than x less than is equal to c. So option E is true. Thus option D is the correct answer, since this only gives us false. The next question is, which of the following is not a characteristic of the normal distribution? Let me first draw the graph of the normal distribution. It is so as we can see pretty much that this graph is symmetrical. So option A, it is a symmetrical distribution. This is true. Now okay, so let me define this graph in much detail. Like as we had done in the previous question, The x-axis, this represents the range of the variables, whereas the y-axis, this represents the probability. Option B, the mean is always 0. This is false. The mean can be anything from minus infinity to plus infinity for a normal variable. The mean, median and mode are equal. Well, for a normal distribution, as it is symmetric, thus skewness is 0. Therefore, mean is equal to median is equal to mode. Option D, it is a bell-shaped distribution. Yes, this resembles a bell, so it is a bell-shaped distribution. Again, this is true. Option C was true. And the area under the curve equals 1. Since the area represents the probability of all the events occurring, which has to be is equal to 1, so the area under the curve equals 1, which is again true. So the correct option is option B. The mean is always 0. This is incorrect. This is false. This mean can be positive, negative, or 0. That does not say, however, that when applying the normal distribution to the real world that a negative mean makes sense or is often seen. You will very rarely encounter a negative mean, but it is true. Again, but you might encounter positive mean and 0 and negative. So it can take any of the values, positive, negative or 0. Moving on to the next question. Which of the following statement is not true for an exponential distribution with parameter lambda? Well, let us first write the PDF of an exponential distribution. If x follows exponential lambda, then PDF fx is equal to lambda e to the power minus lambda x, where lambda greater than 0. Option A, mean is equal to 1 by lambda. This is true. You can calculate the mean as expectation x is equal to x fx dx. So x lambda e to the power minus lambda x dx. If you solve this, this comes out to be 1 by lambda. The standard deviation is 1 by lambda. This again is true. To calculate the standard deviation, you first need to calculate variance x. Variance x is equal to expectation x squared minus expectation x squared. You'll first find out the variance, and from this you can find out the standard deviation as root over variance of x. Option C, the distribution is completely determined once the value of lambda is known. Now see, you calculated the variance and expectation of x by simply knowing the value of lambda. You could calculate the further higher moments just by using lambda, and thus, since only lambda is sufficient to calculate all the moments, this is a one parameter distribution, so this again is true. And since you can determine the distribution only by lambda. Option D, the area under the curve is equal to 1. So let's say if I'll plot an exponential distribution, so say it is something like this. So this area is the probability that all the events occur. So if I take the whole range of X, I will get this to be the total area, which is 1. Option E, the distributor is two-parameter distribution since the mean and standard deviation are equal. Well, this doesn't make sense. It isn't necessary that if the mean and standard deviation are equal, it is a two-parameter variable, or if they are unequal, it cannot be a one-parameter variable. So this actually does not make any sense. So we get the first 4 options to be true and correct, and the 5th one is not correct. Moving to the next question, which of the following distributions is suitable to model the length of time that elapses before the first employee passes through the security door of a company? The options are A exponential, B normal, C Poisson, D binomial, and E uniform. Well, now first, do not consider the time. Just consider what you need to actually see, what you need to actually observe when the first employee passes. Now, for such cases like the probability that an employee passes through the door, you use Poisson for such cases. It is a Poisson process. But for a Poisson process, the time between the events occurring, that is the waiting time, follows exponential process. So, we need to observe the length of the time. This equals the waiting time. Thus, the correct option is option A, exponential. Moving on to the next question. It is known that 20% of all vehicles parked on campus during the week do not have the required parking disk. A random sample of 10 cars is observed one Monday morning, and X is the number in the sample that do not have the required parking disk. We can assume here that the probability distribution of X is. So let us observe the things one by one. It is known that 20% of all vehicles parked on campus. So here you have the fraction or the probability that, what is it? The probability that a single vehicle does not have the required parking disk. That is 20% is equal to 0.2. Now, since we are taking into account vehicles, these are just whole numbers, that is, they range from 0, 1, 2 and so on. You can't have a vehicle say 1.33 or 2.12 or 3.37. This is not possible. So we need to consider a discrete distribution over here. Now coming to the next part. A random sample of 10 cars. Since you have just 10 cars, this is not a big sample, but rather it is a small sample. So in such cases, when the sample is small and for each object in the sample you have a distribution defined for it, we use a binomial distribution. So here X follows binomial n comma p, where n is equal to 10 cars and p is equal to 20%, that is 0.2. So over here X follows binomial 10 comma 0.2. So we can assume that the probability distribution is binomial. Analyzing the other options, we cannot use normal since it is continuous. exponential again is continuous, and for Poisson this is discrete, but say a Poisson has parameter lambda, then lambda is equal to n into p, where n is the sample size almost tends to infinity and p the probability almost tends to 0. Now over here the sample size is small and p is very much bigger than 0. It's quite a significant amount, that is 0.2, so it is not 0. So we cannot use Poisson over here. Any continuous distribution will do? No. Thus the correct option is option A, that is binomial. Moving on to the next question. Which of the following statements are true regarding the normal distribution curve? So once again let us draw the normal distribution curve. Option A, it is symmetrical. Yes, it is symmetrical as we can see from the graph. True. It is bell shaped. This graph represents a bell. So option B is correct. It is bell shaped. True. It is asymptotic in that each end approaches the horizontal axis but never reaches it. This again is true. Well, for a normal distribution, the range of variables, that is x, ranges from minus infinity to plus infinity. That is, even if we take any point on the x-axis, it cannot have 0 probability. Say a number as large as minus 1, 0, 2, 3, 5, 7, 9, 8, 3, 2. Even this has a probability which is greater than 0. So this the y coordinate never is equal to 0, and thus it never touches the x-axis. This curve never touches the x-axis. It goes on like this. Thus option C is true. Option D, its mean, median and mode are located at the same point. Since it is symmetrical, its skewness is actually 0. Thus mean is equal to median is equal to mode. Since all these options are true, thus all the above statements are true, option E is the correct answer. The next question is, indicate which of the statements below correctly apply to normal probability distribution. Option A, they are unimodal. Yes, they have a single mode. It is true. Option B, they are symmetrical. As I had drawn in the previous question, they are symmetrical. So option B, it is true. Option C, they have the same mean and standard deviation. This is false. They can have the same mean and standard deviation. They cannot have the same mean and standard deviation. Option D, the area under the probability curve is always equal to 1. This again is true. Excuse me. Option E, for the standard normal distribution, mu is equal to 0 and sigma is equal to 1. Now for a standard normal distribution, we usually represent it by Z. It follows normal 0, 1. Thus, mu is equal to 0 and sigma is equal to 1. Or rather, sigma squared is equal to 1. So sigma is equal to 1 since sigma cannot be less than 0. So this is true. So the statement which is incorrect is statement C. That is, they all have the same mean and standard deviation. Moving on to the next question. The mean for the exponential distribution equals the mean for the Poisson distribution only when the former distribution has a mean equal to. Now, say, let us demarcate our board first. Exponential and Poisson. Say both have the parameters lambda. Now, the mean for exponential is 1 by lambda, whereas that for Poisson is lambda. For mean of both to be equal, we have 1 by lambda is equal to lambda, lambda squared is equal to 1, so lambda is equal to 1. Remember, lambda cannot be negative. It has to be positive for both exponential and Poisson. Thus, lambda is equal to 1. So, if both of them have 1 as a parameters, the mean for exponential distribution will be equal to mean for Poisson distribution. Moving on to the next question. Which of the following statements regarding the probability density function fx of the uniform distribution is correct? So, say if x follows uniform a comma b, that is the parameters are a and b, then fx is equal to 1 by b minus a, and the graph is represented as such. Say this is point A and this is point B. So the probability would be uniform for each point between this, and elsewhere it would be 0. Hence the name uniform, since all the points in the range of this a to b that are greater than is equal to a or less than equal to b will have the same probability. So now let us analyze the options one by one. The height of the density function differs for different values of x. No, this is false. The density function increases as the value of x increases. We see that the density function remains constant, so again this is false. Option B is false. Option C, the density function is roughly bell-shaped. False. It doesn't assume a bell shape. This is for normal distribution. Option D, the density function is constant for all values that x can assume. This is true. Now we see for all values between a and b, this density function is constant. Thus option D is true. Option E, none of the above statements are true. This is false because option D is true. Thus option D is the correct answer.